Stress is a second order tensor because it maps the normal at a point on the surface to the traction on the surface. So anything that maps a vector into a vector is a second order tensor, and so is the stress, which means that it can be transformed in a manner in which we have transformed all second order tensors. We use our notation for formulating Q. So Q, remember, is cos of old to new. That's what we have decided. And so this is the transformation equation for the new components of stress with respect to the old components of stress. Okay. This should be quite obvious now. We have transformed strains, we have learned about general transformations, and we can transform stresses in the same way. We can of course also solve the eigenvalue problem for the stress and solve the characteristic equation to find the three eigenvalues of the stress tensor. Remember, the eigenvalues are invariants, so it does not depend on which coordinate system you have used to describe the stress tensor, which components you have used, the eigenvalues will turn out to be always the same. Corresponding to the three eigenvalues, which we are going to denote by sigma alpha, there are three eigenvectors, orthonormal eigenvectors, n1, n2, and n3. These are orthonormal vectors, and it turns out that given the relation between traction and normal and the eigenvalues and eigenvectors, we have a very interesting relation between the vectors of the stress tensor and the traction. So we will explore that in a moment. The eigenvectors are also called principal directions, and the eigenvalues are called principal stresses. So um, so uh, the eigenvectors, we have noted this before, that the eigenvectors are orthonormal, which means that they form a bona fide coordinate system. So if I transform these equations, if I find Q such that I go from the XYZ system to the system spanned by N1, N2, N3, then I get the components of sigma prime to be diagonal. And these diagonals turn out to be the eigenvalues themselves, or the principal stresses themselves. So this leads us to what is known as a spectral representation. So we have encountered this before. So spectral representation of stress is sigma alpha n alpha n alpha summation alpha equal to 1 to 3. No summation convention is implied here. So this is sigma 1 n1 dyadic n1 plus sigma 2 n2 dyadic n2 plus sigma 3 n3 dyadic n3. So this is a bona fide representation of the stress tensor. So stress can be represented as its spectral in the spectral manner using the eigen principal values and the principal directions. So when you do that, so this is the spectral representation. When you do that, you let's say you now want to calculate the traction on a plane that has n3 as the normal. So n1, n2, n3 form a coordinate system. So this is n1, this is n2, and this is n3, let's say. And you have a plane in the n2 n3 plane which has plane in the n1 n2 plane which has n3 as a normal, and you want to know the traction on this plane. The way we will do it is we will calculate sigma transpose n3, and then sigma transpose is we can take the spectral representation also. So this is a bona fide representation of the stress tensor. So if we take this, then sigma transpose is sigma 1 n1 n1 plus sigma 2 n2 n2 plus sigma 3 n3 n3, which is same as sigma because it's a diagonal tensor. So this dotted with n3, so everything would become 0, n1 n3 will become 0, n2 n3 will become 0, and you will be left with sigma 3 n3. So your traction vector in the, so we have used the normal in the n1 n2 n3 system, so traction will also come out in the n1 n2 n3 system. So this traction is collinear with n3. So the traction on the n3 plane is actually in the n3 direction. So these principal directions are special directions where the normals and the tractions are collinear. So similarly on the n2 plane, the traction would be collinear with n2, and n1 plane, the traction would be collinear with n1. So traction on a principal plane is parallel to the normal to the plane, and these principal planes are actually special planes on which um, the tractions are parallel to the normals. And there are three such planes because there are three such principal directions. So what is the consequence of the fact that on the plane defined by the normal n3, the traction is sigma 3 n3? The consequence is that this traction does not have any components along the n1 n2 plane. Along on this yellow plane, it does not have any component. The component is purely in the normal direction, which means that when described in the n1, n2, n3 coordinate system, the stress tensor is diagonal. It does not have any um, shear components. It's purely diagonal, and the diagonals are formed by sigma 1, sigma 2, sigma 3, the principal values. In fact, we can take a very special example. The example that I have taken is of a stress that is given like this. There's something here, something here, something here, something here, and something here. These are 0. So in the 3 direction, you have only a normal stress anyway, and in the other directions, you have both normal and shear. Okay, this is the x2 direction. This is x2. So now, if I play this video, uh, this is your point x. This is about which the pillbox is drawn, and rotating the pillbox is equivalent to rotating the coordinate system. So instead of rotating the coordinate system, which is difficult to do in MATLAB, I have rotated the pillbox itself. And while the pillbox rotates, you will see that at some angles of rotation, of course, there are no shear stresses on the third plane anyway, so the third plane does not come into the picture. There's only normal stress in the third plane, which means the third plane is a principal plane anyway. But the other two planes, the first and the second plane, the one plane and the two plane, have both shear and normal. And you will see that as it rotates, so this point is your x, this is, let's say, dx1, this is dx2, this is dx3. And you will see that as this rotates, which is equivalent to rotating this coordinate system, as this rotates, the shear stresses shrink and expand, and the normal stresses also shrink and expand, and there are few locations, few angles of rotation at which the shear stresses completely vanish. So if you see that, if you see it again, you'll see now it vanishes again, and as it rotates, it will keep on vanishing at certain specific angles. Those are the angles which are the principal directions for the plane on which the shear stress vanishes. So those are the principal directions of the plane. Now let us take a problem based on this animation. Let us take a problem where we actually have, stop this. So let's take a problem where we actually have a stress state which is similar to, so this stress state is similar to what we had. So Z is a principal direction, principal plane anyway. The third plane is a principal plane anyway, and you have this. So now finding the principal stresses is easy. You just solve the eigenvalue problem, solve the characteristic equation. So set up the characteristic equation, solve it. You can do that in MATLAB. I have done it in MATLAB, and you get the three uh, eigenvalues. These are the three eigenvalues. These are the three eigenvalues. These are the principal directions. Now, sorry, these are the principal values. These are the principal values. Now we will find the principal directions. Let's find the principal direction for this. What we do is in the characteristic equation, in place of sigma, we place sigma 1, that is minus 105. So we place minus 105 and get this matrix, and we get these equations to solve. Which gives nz1 equal to 0. And if you put nz1, these two equations, by the way, are the same. Both will give you nx1 equal to 1.22 ny1. So one of these two things have to be arbitrary, but we don't make them arbitrary. We take it such that the magnitude of these is equal to 1. So we put the additional condition that nx1 square plus ny1 square plus nz1 square equal to 1. In this case, nz1 is equal to 0 identically, and from this equation and the previous equation we can solve for n1. Similarly, we can solve for n2 and we can solve for n3, and these are the principal directions. Now this principal direction corresponds to 300, which was the stress in the 3 direction, and there were no shear stresses anyway. So this was already a principal direction, and that's why when we solve it, 0, 0, 1, that is the 3 direction, turns out to be one of the eigenvectors, and the other two eigenvectors are n1 and n3, which are all three are orthonormal to each other, and n1 and n3 are the ones that we will look at in a little bit of detail. So let us take n1 for example. N1 is a vector which has x component of x1 component of minus 0.77, x2 component of plus 0.63, and x3 component of 0. So this lies on the x1, x2 plane. This lies on the x1, x2 plane. Okay. So it lies on the x1, x2 plane, and the angle it makes with the x1 axis is minus 40 degree. The minuses got cut off. So if you plot it, this was the x1, x2 plane, and this is your initial state of stress at this particular point. This is given here. I'm plotting the state of stress in the x1, x2, x3 system, which is this. So that is plotted here. And now if you turn this axis to n1, n2, n3 such that n3 and x3 are coincident, and n1 and n2 and n1 are oriented, or n1 is oriented at minus 40 degrees to the x1 axis. So that's what we have found. N2 is oriented at minus 40 degrees to the x1 axis. So we turn it by minus 40 degrees. And now we have, this is your n1, and then we have the other axis, which is n2, which is here. And now we use n1, n2, n3 as my coordinate system. If I use n1, n2, n3 as my coordinate system, then my pillbox is like this. The traction on this particular plane, which is the one plane, is sigma 1 n1, which is minus 105. We know that. and the stress state is completely diagonal. There are no shear stresses anywhere, because this n1, n2, n3 happen to be a principal set of principal directions. So this is the special set of directions in which your state of stress completely becomes diagonal, and there are no shear stresses. Okay, so I hope this explains the concept of principal stresses a little bit more than what you had done in MOS. In MOS, what you did through Morse circle is actually the same thing. You actually transform the coordinates of stresses in a graphical way, but here we do it in a more formal manner. Let us take another example, a slightly more complicated example, but we will do that in the next lecture. Let's stop this lecture here. It's becoming too long. Okay, let's do one more problem on principal stresses, spectral representation of stresses. So we have a plane passing through a point P, and it has a normal n, and you have the stress tensor at that point P, and you have to find the value and direction of the maximum shear stress that acts on the plane, maximum shear stress that acts on the plane. So this is how we can go about it. So let us write the stress tensor in. So we have this plane here. The normal is n, and now we have taken the arbitrary set of axes given by n1, n2, n3. These are the eigenvalues, and then we can write the stress in this manner where no summation is implied. So sigma 1 n1 diatic n1, it's a diagonal, n2 diatic n2, and so this is the representation of the stress in the n1, n2, n3 coordinate system. So now we can represent the normal, this vector n, in terms of its components. So n we also write in the same coordinate system as n1, n1, is n2, n2, n3, n3. So n1, n2, n3 are the coordinates, are the components of the normal. Now let us write the traction. Traction is sigma transpose n, and if you take the transpose of this, you get the same thing, and then multiply it with the normal. So so if you do that, this is this is what you will get. Sigma 1, sigma 2, sigma 3 are the eigenvalues of the stress, and n1, n2, n3 are the normals expressed in terms of components in the space spanned by the principal directions. So this is your traction, and now what is the normal component of the traction? The normal component of the traction is simply t dot n. So that is the normal component of the traction. Let's call it sigma n. So t dot n we can easily calculate. So we dot this with n, and then we will get. So this is wrong. This is n2. This is n3. Okay. So if we dot t with n, we will get the normal component, and this is the normal component after dotting t with n, and this is what it turns out to be. So remember, sigma transpose n is t, and we have calculated it as sigma 1 n1 n1 plus sigma 2 n2 n2 and sigma 3 n3 n3. I hope I'm not making a mistake. Yeah. And n is n1 n1 plus n2 n2 plus n3 n3. So if you dot it, you will get this. Now, um, you can of course do a lot of things to get the component along the plane. So what we are looking for is we have the traction, which so on this plane we have the traction vector t, and we have taken the component Tn, and now we will take the other component which we call Ts, and what we are interested in is tau s, which is the magnitude of this component Ts. So to take this component, what we do is take this component Ts, what we are going to do is we are going to take the whole vector and subtract the normal part. So we know that uh, this Tn and Ts, if we form this triangle, then modulus of Tn square plus modulus of Ts square, so Tn square Ts square will be equal to modulus of T square. So T is here, so we can calculate T square, and Tn we have calculated. So Tn we have calculated, the vector Tn is sigma n times n, okay, and Ts would simply be the difference between the two. So Ts square we will calculate as, so Ts square would be T square minus Tn square. That's what we are going to do to get this, get the magnitude of this component of the vector. So this is what we have done, and then Ts square is tau square, which comes out to be this one. So we want to know that when will this be a maximum, what would be the value of n1, n2, n3 for which it has to be a maximum. And to do that, what we are going to do is we are going to take the derivative of this with respect to n1, n2 and n3. We actually don't have to take it with respect to n1, n2, n3, because we know that n1 square plus n2 square plus n3 square is equal to 1. So we need to choose only two of these as independent variables, and the other becomes a dependent variable. So we'll choose n1 and n2 as the independent variables and n3 as the dependent variable. So we will set del tau square del n1 as 0, del tau square del n2 as 0. So once you've got n1 and n2, from this you will be able to find n3. So that's what we do, and this is what we will get. You can work it out. I think these expressions are correct. So we have taken n1, n2 as independent quantities, and then from this equation we can find n3 once we know the n2. So we set this equal to 0 because we are trying to find out the n1, n2, n3 components for which tau square is a maximum. The obvious first choice for this being equal to 0 is n1 equal to 0, n2 equal to 0, which gives n3 equal to 1. Remember, we have chosen n1, n2 to be independent and n3 to be dependent. We could have done other things also. We could have chosen n1 to be dependent, n2, n3 to be independent. We'll get similar two equations, and then n2 to be n2 to be dependent and n1, n3 to be independent. Again, we will get two equations. So we will get 6 such combinations. But for these two combinations that we have on the slide, n1 equal to 0 and n2 equal to 0, and therefore n3 equal to 1 is a solution. So if we take that solution, then we will see that for that solution, tau turns out to be 0, which means that the shear stress on the plane is equal to 0 for this choice. For the choice n1 equal to n2 equal to 0 and n3 equal to plus minus 1, shear stress is equal to 0, and the normal to the plane is in the plus minus n3 direction. Similarly, if we take the other two combinations where n1 is n1 is plus minus 1 and n2, n3 is equal to 0, we will get this choice. For n2, we'll get this choice, and this choice we have already proved. So these are the 6 possibilities for which there will be the shear stress on the plane will be equal to 0. That is obviously not a minimum, that is a maximum. That is not a maximum, that is actually a minimum. Okay, so this choices give us the minimum and not the maximum. Now what we can also do is we can fix n1 to be equal to 0. If we choose arbitrarily fix n1 to be equal to 0 uh, and assume that the eigenvalues are distinct, sigma 2 and sigma 3 are sigma 2 minus sigma 3 is not equal to 0, then we get n2 is plus minus 1 by root 2 from the second equation. So uh, we use this equation, sigma 2 not equal to sigma 3, so this is not 0, so we use this, and using this we get the fact that for uh, we get the fact that for n1 equal to 0, n2 is plus minus 1 by root 2, and then because square of this plus this will have to be 1, n3 is also plus minus 1 by root 2. Okay, obviously other two sets are possible. We can take n2 equal to 0 and n3 equal to 0 also. We in For n2 equal to 0, we have to assume that sigma 1 is not equal to sigma 3. For n3 equal to 0, we have to assume that sigma 1 is not equal to sigma 2. So these vectors are planar and make angles of pi by 4 with the in-plane axis. So when I take n1 equal to 0, I have n2, n3, so these vectors lie on the 2, 3 plane and make an angle of plus minus pi by 4 depending on whether you are taking 1 by root 2 or minus 1 by root 2 in the 2, 3 plane. Okay, so just one more point is we have restricted ourselves to the case where sigma 2 not equal to sigma 3. If that was violated, then what would the eigenvectors be? I leave this as an exercise for you to think. What would the eigenvectors be? We now proceed with the situation where sigma 2 is not equal to sigma 3 and n1 is equal to 0. So in this case, these are the solutions that you will come up with. These are the possible solutions for all the cases that we have. So for n1 equal to 0, this is for n2 equal to 0, this is for n3 equal to 0. So in this case, n2 is plus minus 1 by root 2, plus minus 1 by root 2, and in this case n3 is plus minus 1 by root 2, and tau square turns out to be this, or this in these 3 cases. Now what we see is that one of these have to be the maximum, and the maximum would depend on which of these are the larger. So the difference between the largest and the smallest, so if you are arranging the eigen values in this manner, then the difference between the largest and the smallest will give you the maximum. So tau square will be maximum. You have to take the maximum of sigma 1, sigma 2, sigma 3 and minus the minimum of sigma 1, sigma 2, sigma 3. That will give you the maximum value of the shear stress. If you arrange the eigen values as sigma 1 greater than sigma 2, sigma 3, then this would be your maximum shear stress. This would give you, or the root of this will give you the maximum shear stress. Okay, So this is the solution to this problem. The maximum shear stress occurs uh, in the plane spanned by the maximum the eigenvector corresponding to the maximum eigenvalue and the eigenvector corresponding to the minimum eigenvalue at a direction of 45 degrees to the axis. What I mean is that if I assume this, then the maximum is this, minimum is this. So I have to go to this plane. So I have to go to the N1, N3 plane, okay, and the maximum shear stress would occur if N is along these directions. N makes an angle of plus minus 45 degrees with N makes an angle of plus minus 45 degrees with the N1 and N3 axis. If if something else, if this is the maximum and this is the minimum, I have not arranged it like this is the maximum, this is the minimum, then we'll have to go to the 2-3 plane, and then the maximum principal stresses would occur along the 45-degree directions. If you go back to your Mohr circle, you will remember that this is the same conclusion that you had reached for the maximum principal stress. In the Mohr circle, the maximum principal stress, maximum shear stress, I'm sorry, this is the maximum shear stress. The maximum shear stress occurs at an angle of 45 degree to the directions of the maximum principal stresses. Okay, the maximum shear stress occurs at an angle of 45 degrees to the maximum shear stresses. When you drew the Mohr circle, you were necessarily dealing with a two-dimensional state of stress. And in a two-dimensional state of stress, you had only two eigenvectors, two eigenvalues, and therefore your plane on which the maximum and minimum occurred was unique. In this case, you have three, so you have three sets of planes on which you can have a maximum, one of which can have a maximum minus minimum. So that plane, if that is the 1-3 plane, then 45 degrees to either axis, you will get the directions in which you will have the maximum shear stresses occurring. Okay, this finishes our discussion on the concept of stress, and now we are in a position to look at the complete problem. So we have done kinematics, which is the strain displacement relations. Now we have looked at stresses as well, and now we start putting it all together to frame the boundary value problem that we need to solve if we want to solve a problem in elasticity that we start in the next week.